Welcome back to G Fun Facts Online. The universe has a specific talent for humiliating us. Just when we think we have the physics pinned down, it throws a curveball. For centuries, astronomers were convinced they understood the humble comet. We called them dirty snowballs. We viewed them as primordial lumps of ice and dust, tumbling in from the frozen dark, only coming alive when the warmth of the sun sublimated their surface into a glowing tail. We thought of them as cold, quiet relics. But in 1996, the universe whispered a secret that changed everything. A German satellite named ROSAT was scanning the sky. Its job was to look for the violent signatures of black holes and supernova remnants. On a whim, the team turned its gaze toward a comet passing by Earth named Hyakutake. The scientific expectation was silence. Comets are cryogenic objects. They are too cold to emit high-energy radiation. But instead of silence, the detector lit up. The comet was screaming in X-rays. That discovery birthed an entirely new field of astrophysics. Today, as we stand here in December 2025, analyzing fresh data from the Interstellar Visitor 3I Atlas, we finally understand that this phenomenon is not just a curiosity, it is a window into the very nature of our solar system's interaction with the galaxy. This is the story of Cometary, Bremsstrahlung, and charge exchange, the physics of how frozen interstellar ice becomes a generator of high-energy light. To understand why X-ray emissions from comets were so shocking to the scientific community, we first have to appreciate the energy scales involved. The visible light of a comet, the beautiful tail you see in the night sky, is merely reflected sunlight or the gentle fluorescence of gas molecules excited by UV rays. These are low-energy processes involving just a few electron volts. X-rays, by contrast, are the currency of violence. They are typically born in the infernos of accretion disks, the shock waves of exploding stars, or gases heated to millions of degrees. A comet nucleus is a cryogenic object, drifting at temperatures near absolute zero for most of its life. Even when it becomes active near the sun, its atmosphere, or coma, rarely exceeds the temperature of a pleasantly warm day on Earth. For a comet to emit X-rays is akin to finding a block of dry ice in your freezer glowing with the intensity of a welding torch. This is the paradox that confronted the ROSAT team on March 27, 1996. Comet Hyakutake passed close to Earth, and largely on a whim, they pointed the high-resolution imager at it. The resulting image was undeniable. It showed a crescent-shaped emission of soft X-rays, strongest on the sunward side of the comet, with a total power output of nearly a gigawatt. This wasn't a flicker. It was a beacon. The discovery sent theorists scrambling. The initial guesses were imaginative but flawed. Some asked if it was the sun's X-rays reflecting off the comet's dust. The math didn't work. The reflectivity required would be impossible. Others asked if it was Bremsstrahlung. Bremsstrahlung is a German term meaning breaking radiation. It describes what happens when a charged particle is suddenly decelerated by another charged particle, releasing its kinetic energy as a photon. While plausible, the source of electrons energetic enough to cause this was a mystery. It took years of modeling and the arrival of more sophisticated observatories like Chandra and XMM Newton to unravel the true dominant mechanism. It turns out to be a process that links the ice of the comet directly to the wind of the sun. While Bremsstrahlung is the catchy title often used to describe the broad class of breaking radiation, the primary engine of cometary X-rays is a specific, elegant dance called solar wind charge exchange, or SWCX, though true Bremsstrahlung plays a crucial, darker role in the background. Let's break down the mechanics of this invisible light. The story begins with the fuel, the interstellar ice. Comets are time capsules, composed of volatiles frozen since the birth of the solar system. We are talking about water, carbon monoxide, carbon dioxide, methane, and ammonia. This is interstellar ice, created in the cold molecular clouds that predated our sun. As the comet plunges toward the inner solar system, solar radiation heats the nucleus. The ice doesn't melt, it sublimates, turning directly from solid to gas. This expands explosively, creating the coma, a tenuous atmosphere of neutral atoms and molecules that can extend for hundreds of thousands of kilometers. This coma is the target. The bullet is the solar wind. Streaming from the sun is a relentless gale of plasma moving at supersonic speeds, anywhere from 300 to 800 kilometers per second. This wind is not just protons and electrons. It is a soup of highly stripped minor ions. These are heavy elements like oxygen, carbon, and nitrogen that have lost almost all their electrons in the searing heat of the solar corona. These ions are chemically ravenous. They are desperate for electrons to return to a stable state. When a highly charged solar wind ion, let's say an oxygen nucleus missing 7 electrons, crashes into a neutral water molecule from the comet's coma, a theft occurs. This is the charge exchange. The ion rips an electron from the water molecule. This stolen electron is captured into a high, unstable energy orbit around the oxygen nucleus. It is like a ball caught on the rim of a funnel. Almost instantly, the electron cascades down to the lowest energy state. As it falls, it sheds its excess energy in the form of a high-energy photon, an X-ray. Because the solar wind contains many different species of ions, and each emits a specific color or frequency of X-ray when it captures an electron, the comet acts as a spectrometer. By analyzing the X-ray spectrum of a comet, we are actually tasting the composition of the solar wind at that specific location in space. However, we cannot ignore the role of true Bremsstrahlung. While charge exchange dominates the soft, or lower energy X-ray spectrum, Bremsstrahlung remains a vital player, particularly in the high-energy, hard X-ray regime. When the solar wind slams into the cometary obstacle, it creates a bow shock, similar to the wave in front of a speedboat. In this turbulent region, magnetic field lines tangle and snap, and plasma waves froth. This turbulence can accelerate electrons to tremendous speeds, reaching energies of kilo-electron volts. When these superaccelerated electrons impact the neutral gas of the coma or the solid dust grains, they are rapidly decelerated by the electric fields of the atomic nuclei. They break hard. This rapid deceleration releases true Bremsstrahlung X-rays. Recent laser plasma experiments, like those conducted at the L'Uali facility in France, have simulated this environment. They proved that in cases of violent interaction or high solar activity, Bremsstrahlung can contribute significantly to the comet's glow, particularly explaining anomalous high-energy emissions that charge exchange cannot account for. Now, let's fast forward to the present day. The date is December 10th, 2025. The astronomical community is currently buzzing with the first confirmed X-ray detection of an interstellar comet, 3I Atlas. Unlike Halley or Hyakutake, which were born in our own Oort cloud, 3I Atlas is a drifter from another star system, ejected eons ago to wander the galaxy. Its arrival in our solar system offered a unique test. Would alien ice interact with our solar wind in the same way? The answer, delivered by the XRISM satellite, is a resounding yes, but with a twist. The X-ray signature of 3I Atlas is subtly different. We are seeing a distinct suppression of carbon emission lines compared to oxygen. The charge exchange mechanism relies on the neutral atoms in the coma. If the comet's ice has a different chemical ratio than our local comets, the X-ray spectrum will shift. This result suggests that the interstellar ice of 3I Atlas is depleted in carbon chain molecules compared to the standard solar system recipe. We are effectively doing chemical analysis of a star system light years away, using our own sun's wind as the probe and the comet as the sample slide. This brings us to the practical application of this physics. Comets are essentially solar windsocks. The solar wind is invisible to the naked eye. We can measure it near Earth with satellites, but we have very little idea what it is doing out near Mars, Jupiter, or above the sun's poles. However, when a comet passes through these regions, it lights up. By watching the flickering intensity of a comet's X-rays, astronomers can see gusts and lulls in the solar wind in real time. We have observed comets losing their X-ray tails or brightening suddenly when crossing the heliospheric current sheet, which is the magnetic equator of the solar system. Furthermore, if a coronal mass ejection, a massive solar storm, hits a comet, the X-ray brightness can spike by a factor of 100. This allows us to track the propagation of these storms through the solar system in 3D. The realization that cold ice plus hot wind equals X-rays has profound implications for the future of astronomy. We are looking at mapping the solar system's shadow. The outer solar system is full of icy bodies. While they are too far for the solar wind to cause intense X-rays, the local interstellar medium, the gas between stars, also flows through the solar system. We are now building telescopes to detect the faint X-ray background caused by the solar wind hitting neutral hydrogen from interstellar space, a glow that permeates the entire heliosphere. Even more exciting is the prospect of exoplanetary comets. If comets in our system emit X-rays, then comets in other star systems should too. Massive exocomets plunging toward young, active stars, which have much more powerful stellar winds than our Sun, might produce X-ray flares detectable from Earth. This could be a new method for detecting water-rich bodies in alien solar systems. And closer to home, the Bremsstrahlung connection has sparked a renaissance in laboratory astrophysics. Scientists are firing lasers at ice targets to simulate the solar wind, helping us understand not just comets, but the fundamental physics of plasma-neutral interactions that occur in supernova remnants and tokamak fusion reactors. In conclusion, the phenomenon of cometary X-ray emission is a beautiful contradiction. It requires the deepest cold to produce the target, and the fiercest heat to produce the projectile. It reminds us that in space, nothing exists in isolation. A lonely chunk of ice, adrift for billions of years, eventually meets the breath of a star. In that meeting, energy is exchanged, electrons dance, and for a brief moment, the frozen ghost of the solar nebula shines with the light of a dying star. As we analyze the data from 3i Atlas this week, we are reminded that the sky is not silent. It is filled with these invisible conversations, waiting for us to tune in. The ice is speaking, and in the language of X-rays, it has quite a story to tell. Thanks for listening to G Fun Facts Online.